I'm going to show you how CPU to CPU communication can be configured on PROFINET PROFIsafe using Automation Builder version 2.1. In this example, we'll show you configuration with two master systems, which are connected to one so-called shared slave. You can see this in this overview. The master one includes CM589 CPU and in addition safety CPU CM589-S, and the master 2 PM583 includes this CPU module and safety CPU SM560S. These are both safety CPUs which we have already on our portfolio, but on the slave system, on the shared slave system, we will use new safety CPU, which is SM560S F-Device and new communication module PROFINET IO device CM589-PNIO-4. It means when we mention in the name of these modules a number 4, they can handle up to 4 master communications simultaneously. In this example, for simplicity, we'll present only 2 connections, but in a similar way you can also extend them to up to 4 connections. In the next step we are going to switch over to Automation Builder project. I've prepared 3 projects for 3 safety CPUs with all basic configuration which is needed. It means that typical steps which are needed to configure the standard CPU and also safety CPU are already done on master system, master system 1 and master system 2, and on shared slave we are starting from the standard CPU and IO modules, and new communication module will have to be added and the new safety CPU have to be added. I will show you this and how to do this. So now we are changing to the Automation Builder. Here you can see an overview. We've included 3 different CPUs, and as I mentioned before, with the basic configuration we have master 1, which includes PM595. On the IO bus we have one DX581-S module, which has on board 8 safety inputs and 8 safety outputs. We will use safety outputs of this module. This is what you can see in the IO mapping list. I've added this variable s_master out byte DX581 as a byte, which allows us to set some values on the digital outputs and see that these values are changing. The values will come from the slave system in this example, and the other master system will pass by the predefined values to the slave so that it can further pass it by to the master 1. I will come back shortly to the overview picture. It means what we are going to show is that master 2 has some counter value which will be transferred both using PROFINET standard communication to this standard program, and the safety counter which will be transferred also to the shared slave system, and it will be both these values will be visualized here on these modules. So the standard process values on the DC523 IO module with also include configurable standard inputs and outputs. We'll use the outputs for this purpose to see that LEDs are blinking, and the same thing we'll do with the safety output module. In addition to this, we'll further transfer these values to the master 1 system so that the master visualizes, in this case, only safety counter value on its DX581 module. So again, the expected behavior is that the LEDs will be blinking with some values which are predefined by the counter which is running on the master 2. So what you can see here is that you can both exchange input and output values, safety and standard process values with one master, and at the same time simultaneously exchange them with master 1. And as I mentioned in the beginning, we can extend this similar behavior with up to 4 master systems. The maximum number of bytes which can be exchanged by the shared slave is 1440 bytes, and out of this 1440 bytes, 384 bytes can be allocated for safety data. And these bytes can be split between 4 master systems. Now we're coming back to the Automation Builder project. As I mentioned before, so we have the second master system, which is master 2. It has no I/O modules, as you've seen, so it will be our predefined counter preset value, which will transfer further to shared slave, and then from shared slave to the master 1 for visualization. If you have a look at the master 2 project, we have PROFINET IO master here, which is an external communication module, and the safety CPU. In case of master 1, we use onboard PROFINET IO master functionality, which you can see here, and then have only safety CPU plugged in as an external module. The slot 2 is not occupied. The TA524 module can be used to cover this place. So now we start with the configuration of the slave. The slave at this point has only these 2 I/O modules. As I mentioned in the overview picture, we want to visualize the transferred process values from the master 2 system on the DC523, and also the safety relevant values on DX581S. Therefore, if we click on this module, go to the I/O mapping, you can see that for outputs, again, we reserved 1 byte for all 8 safety outputs on DX581S, and on DC523 we also reserved a byte to visualize the process values, and we call it byte visualize DC523. So the next step would be, as if you look at the extension bars, there are 2 empty slots which were specially reserved for our new safety CPU and a new PROFINET IO device communication module. We'll start with the safety CPU. If you click on slot 1 and select Add Objects, in Automation Builder version 2.1 you see that you have not only the CM589-S safety CPU, but also the modules with FD1 and FD4. If you would need the communication to only one master system, you could select FD1, it would be enough. But since we have 2 master systems to which one we want to communicate simultaneously, then we have to select the FD1 version. We select it. The default user authentication is needed. We use the standard owner with the empty password, which can be later on configured in the project with a real password. And the next step would be to add CM589-PNIO-4 PROFINET IO device module. You can see it in addition to the previous one, which is CM589-PNIO, which was launched 2 years back in 2015. And now we have the version -4, Again, since we wanted to communicate as a slave to more than one master system, we have to select the version with -4. Now the first step we have to do is to enable debugging for our safety CPU. So we select this value to on to be able to load the boot project on it. And on CM589-PNIO-4 we can modify the min update time, which are standard parameters for all communication modules. We'll leave it for this demo system at 10. It could go up to 1 millisecond. For our PROFINET IO device, we have to set a PROFINET name. The PROFINET name will be automatically set, in our case, using the principle which is shown here. The default name is CM589-PN and then minus, here you can see 00. We'll use the address switch on the CM589-PNIO-4 to set the PROFINET name, and therefore it will be automatically assigned. In our example, we set the address to 5, the lower address switch, which means that the PROFINET name of the device will be CM589-PN05 when we start the project. The same PROFINET name will be used for all master systems. So the shared device functionality allows to share the data for one PROFINET device with up to 4 master systems in our implementation, and it uses the same name and the same IP address. It means, of course, that due to the fact that this IP address will be set by the default master system, all masters will have to be in the same IP address area to be able to talk to this PROFINET device simultaneously. For your information, the virtual LAN functionality is also supported by PROFINET. You have to configure this virtual LAN tagging on your network switches. You may need manage network switches and activate related ports on it to be able to send these VLAN tagged telegrams to proper LAN network paths. However, we have to take into account that PROFINET requires in the beginning untagged network to be able to parameterize all participants. So with VLAN tags, one has to pay special attention to the network switch configuration for PROFINET. Now the important task comes here is to instantiate data areas for standard and safety data exchange between master and slave systems. So here we will use 4 bytes of output data to receive input values from master 2. As you can see, these are inputs. So for slave system, these are input data. From the IC program part, these are input data, which are the output data for the master system. So the master sets this data as outputs for our shared slave, and then they are assigned as inputs inside the program. One of these bytes, let's call it, we can assign already here the name, which would be the byte from master 2. These are the data which we are going to show on our DC523 module. And then, to transfer this value further to master 1 system, we will add 4 bytes of input data, which is the output to the master system. Means we'll assign here the name byte to master 1, so that the master 1 also receives these data which is passed by from master 2 to the slave system. I will save here the project. The same thing we'll have to do with the safety data. As for safety data, we have here two options. One is 12 bytes in out data, which is the standard PROFIsafe telegram with a short frame, and then there is another data type which was developed for all the Siemens safety CPUs S7300 family. The newest 1500 family support also 12 bytes in output. As you can see, the PROFINET PROFIsafe communication and the slave functionality can work not only with our AC500-S master systems, but also with third-party ones from Siemens or Phoenix Contact. Again, we'll instantiate 2 times 12 bytes of safety data. One is for master 2 and the second one is for master 1. We'll define the names. First we'll need the name for the input byte. This is the data which we are going to visualize on safety outputs of DX581S module. Let's call it S byte from master 2, and then we have to send some data to master 1 system, and here we will have to use the outputs because the data goes out from our safety CPU, and here we say S byte to master 1. Now we are complete with the configuration of the shared device system. What we have is allocated the data areas for data exchange. The first one and the third one, standard and safety, will be used for master 2, and the second one and the fourth one will be used to communicate the data with master 1. Now we can create check configuration, create safety configuration data, and do the same for our standard project. As you can see, standard message boxes come to confirm that safety libraries, proper versions of them are used. You have to look at the CSC value of them. This has to be done only once in the project. As soon as the libraries are confirmed, their CSCs are saved in the safety project, and then you are not asked anymore to confirm them other than they are changed on your hard disk, and then you have to confirm if you want to keep them or then replace with proper versions. So now we have our safety project. I will import here for simplicity the watchdog configuration file, which is the startup procedure to configure the watchdog cycle time supervision on the safety CPU to 10 milliseconds, and then call this as a function block, as a program subprogram from the PLC PRG. Now what we have to do is, first we'll have a look which kind of variables we have in the safety program. If you look at the inputs, we have this byte of data which we receive from the master2 system, and we have two outputs. One of them we use to assign this received byte to our DX581-S module, and the same data we want to send to the master1 system. So we have to do this simple assignment in the application program. We'll do this for simplicity directly in the PRG. Assign received value to master1, and the same will do to visualize them on the DX module. We'll copy the same value to this variable and DX as outputs. So now we are done on the shared safety program part. The same thing we want to do on the standard process part. Do the clean all, rebuild on for the project. And then later on we'll download this to the CPU. At this time we'll switch over to the standard project. The configuration has to be updated. And here, if you want to have a look on which variables we have, you can see that PNIO-4 device is included here, and all 4 modules are present. Here are the variables which we defined for safety, and these are variables which we defined for standard data, non-safety data. So our task now is to assign this byte which we receive from master2 to the outputs on DC523 non-safety module. Which we can see here, to visualize them, and then at the same time to send them to the master1. So we'll go to the PLC PRG and again do these 2 assignments. First we'll use the byte which we are going to send to master2. And then we want to visualize. For this purpose we use the byte visualize and can copy paste this part. Visualize on DC522. So we are done here as well. Have to clean all, rebuild on, and now we can download this project on our CPUs. So now we connect to the PM5A3, download the new program, and then create a new boot project. The same we'll have to do for safety. We are ready with the safety project on our shared slave system. What we have to do is to download it and then create a boot project. We just have to power off and power on the system so that they get active. What we've reached at this level is we've fully configured the shared slave system. It has 4 communication modules which we instantiated. One is for our master 2 system, for non-safety part. Then the second one is for our master system 1, which will receive this byte further to visualize it. And then we have 2 safety communication modules. One is from master 2, again some predefined counter value, which we want to visualize on our DX581S module on the shared slave. And then the second one is to transfer this value further to the master 1 system, again to visualize it using LEDs on safety digital outputs. The PROFINET name was defined using address switch, and the F parameters for the safety modules will be downloaded by each master system when we define which of them is responsible for which module. For your information, the PROFIsafe addresses which we are going to set at this level, I selected used the address switch on CM589-S FD4, and I set the low value to A, which means that the addresses for PROFIsafe instances start from 1000 and go up to 1031, because 32 instances is the maximum supported by the system. Now we go to the master system 2, and at this stage we go to the PROFINET master, and we have to instantiate here the instance of CM589-PNIO-4. This is what we can see here. We add this object, and now we have to create the same data which we created on the shared slave system. We create 4-byte output and then 4-byte input, these are non-safety data, and then 2 times safety telegrams. Here you can see that the safety modules are also shown with yellow background, because they will have also F parameters here. The safety modules which we instantiated on the slave system, these were just containers, and here we actually will provide F parameters to configure these modules. So we instantiate 2 instances. Now we can define in the project first the addresses for F-Devices. So here you can see that there is a source address which we have to set, and we can take it as 1. The source addresses of master systems have to be unique. So let's go for value 150 here. And then define a destination address based on the value which I selected on the address which we have to start with 1000. The watchdog time we keep it as it is with 100 milliseconds. The rest of the parameters can be kept without changes. And the next module, which we don't plan actually to control, we don't necessarily have to configure, but since this configuration which is done here can be copy pasted also on the master 1 system, and it has to be the same and have the same data types and size of data as we defined in the shared device, then we can still do this already at this stage also the proper configuration, so define a source address of 151 in this case, so one more than from master to system. And then the next address, destination address we have to take is 1001. It's 1000 plus 1 basically, and if you instantiate further modules, then you add again plus 1 up to 32 instances you can instantiate overall for all masters. So we end up with a 1001 here. The F-pass CSC is automatically calculated for F parameters, therefore there is no need to do any copy paste. The safety CPU with F-Device functionality, they don't have any E parameters, therefore you don't have to do any E-pass CSC calculation. This is slightly the difference to safety IO modules, which have also E parameters which have to be defined, therefore you have to do F-E-pass CSC calculation. Now we can define variable names. So this is the output byte which we are going to read at our slave, and will provide us the counter value which we decided. So it's a non-safe value, we take it as a byte counter for slave. And then this value we actually don't want to use again on this master system, but we can still define the input variable. It will be used on the master 1 system, because whatever we configure here we'll just copy paste it to the master 1 system. Therefore we'll define already here the byte input from slave, and this is the value which we'll read on the master 1 system and can visualize also if we have some standard IO module, and for safety we'll do a similar thing. We go here for safety modules. Here first we want to write the value, so we take the output byte 0 and say s byte for slave. This value will be written, and the next one is the value which we are going to read, the master 1 system, so it's s underscore byte input from slave. So therefore we can show here in parallel that both safety and standard data can be simultaneously transferred between master systems, and in fact it's in both directions. Here we just simplify it and use one direction from master 2 to slave and from slave to master 1, but you can simultaneously read and write data. Now we will copy first all configured modules from master 2 projects in master 1, because they have to be present there as well, independently if we want to use them or not. So you can see we just copy pasted them, and now we can check that they're present, right? Now we can decide which of them will use which. So we'll start with master 1, and we said that this output byte we're not going to use in the program, so we disconnect the module. And the same is true for the first safety module, so we disconnect it again. Now the same thing we have to do, but slightly different on the other side. Here we won't use the output, so we keep it, and input we disconnect, and then we disconnect the second safety module because it's actually used on the master 1 system. And now there is one important step which have to be done to complete the master configuration. We have to define the PROFINET name. As you remember, on the slave side we used the address switch with the value 5, So we have to enter here 5. We'll save it. And the same we have to do on the CM589-PNIO-4 in another project on master 2. You would have to do similar things also if you would use third-party master systems like Siemens. And now you have to define the primary shared device controller here. This value you can select at this stage. You have this select box, checkbox, which you can use. It is important that only one of master systems, it could be up to 4, in our case we have 2, have this deselected. All others have to select this. So what we'll do, we'll select it here. It means that on the other master system this parameter can be deselected, which is okay. It means that this device will have to put the primary configuration for shared device to the PROFINET IO device with shared device support, which is shown in this shared device project. Now there could be a question, what happens if this primary master is not available? No problem. The PROFINET IO device has default configuration, which is okay to start the communication also with the masters which are available, even if the primary master, which was deselected, is not there. You will also get some diagnostic message at this level, which will inform you that the primary master was not used to configure this module, but it doesn't necessarily jeopardize the availability of the application. Now that we finalize the configuration in the project, we have to pay special attention to the setting of IP addresses for PROFINET master and PROFINET IO devices. Let's have a closer look on our PROFINET IO device CM589-PNIO-4. As I mentioned before, the IP address is set on master project. So if you have more than one masters which are communicating with this device, then you have to pay special attention that the IP address is the same which you set for this IO device. For example, if we go to the master 2 project, we click on CM589-PNIO-4 device and see that the IP address which we want to set for this module is 192.168.0.2, and the subnet mask is the one which you can see, and the PROFINET name is this one based in the address switch. Now when we go to the PROFINET IO device configuration in master 1 project, again we have to have a look and see that the same PROFINET name is set and the same IP parameters are set. If you have some third-party master system like Siemens or Phoenix Contact, then you have to be prepared that you have the same settings there as well. If you don't follow these rules, you'll have some configuration error on the master system. And as a second step, we also have to have a look on the master and the master addresses. So the IP addresses of masters have to be within the same address range, but have to be unique. It means that the PROFINET IO controller on the master 1 has to have this address, and this is the address settings for slaves, so the area can be defined here. And at the same time, the other master, it has to start from the other area, and the IP address settings for slaves can have the same range on both master systems, but their own IP addresses have to be unique. This is what you can see. Here we have the last value is 200, and on the other master system we have it set to 1, which is exactly as we expect. So now the project is also properly configured for IP settings. So now we are done with the configuration. The only thing left is to create valid boot projects, non-safety, safety on two master systems, and assign variables respectively to the I/O modules, non-safety or safety I/O modules, to visualize the status of the counter. So we'll start from the master 2 because it is the source for the counter. What we'll do, we'll open up the non-safety project. I will create the following small program. We will use the 4-byte output and simply do the counting operation with it. Count it by 1. Okay, now rebuild all. In master 2 we don't have any I/O modules, so we only transfer this value from the safety program. What we'll do, we'll log into the CPU, download this new project, and create a boot project. When the boot project is created for non-safety, we can do the same for safety part. So we'll start a safety project. And add one line of code, which we will do a similar thing with the safety byte. We'll increment it by 1. Structure text for safety, which is supported by AC500-S. You can do a similar thing, of course, in functional block diagrams. And then download this. Finally create a boot project. Now we are done with the master 2. Now we have to do similar thing with master 1. We'll start the non-safety project. Update it. So in the non-safety project, since we don't have non-safety I/O modules on master 1 system, we will not visualize the values coming here. We'll just assign it to a temporary variable, which we can define. Assign it to byte, and then use it to get the value from the as input from slave. This is all we have to do. We have a valid project which will have to be again downloaded to the standard CPU. The boot project will have to be created, and then we are done with the non-safety part. Now we go to the safety project. Take a safety CPU on master 1 system. We'll go to the main PLC PRD, and here we have a safety I/O module DX581S. So we'll use use it output to visualize using safety output channels and LEDs what we receive from the slave system. Save the project, clean all, rebuild all. We'll download again the project to the safety CPU. And then create again the boot project. So the configuration is complete. After restart of the system, we shall observe the blinking of the safety output modules on the slave and master 1 system, and then blinking of standard output channels on DC5 to 3 non-safety IO module. The source of this information is coming from master 2 system. So you can imagine that in a similar way you can also create more complex communication. Now we've successfully completed the project with the usage of CM589-S FD4 new safety CPUs and new communication module CM589-PNIO-4 to be able to exchange data between different CPUs.